we described the one-loop partition function, just a vacuum one-loop partition. We understood the modular invariance, blah blah blah. I haven't come up with I haven't tried to come up with better arguments for that modular invariance. So I did check that one can pass on with some. Okay, once you express that partition function in Boolean. You see, there are two ways of writing the partition function that we did. Think of it as coming from quantization of the fermions, which is the way we do it. But you can also think of it as coming from the quantization of bosons. See, the pairs of fermions are bosonized. Okay? And actually that partition function is nicer because the oscillator part is just like an interaction. Okay, the oscillators are the oscillators. Okay? The only thing that's different is the zero mode part. Okay? Which admits a simple Poisson expression. It gives you what you want. Technically it's easy to show this thing. There's probably a better physical argument which I haven't read. I haven't done. Now, just write down a formula for the partition function thinking of it in terms of x. Okay? So there are all the states that come from the zero modes. Those are shifted momentum. Vacuum has some shifted momentum, e to the power is minus I alpha by 2 or something like that. And then you have all the integers, you multiply by e to the power I h for every integer. Okay? So you've got a sum from all possible contributions to the zero mode. What do you not mean?
I mean, we had a general mod. Okay, we had a general period of 5.
Yeah, so we know the answer. You see, what I'm just doing is counting every operator. So what are the operators in the game? The operators are the vacuum, and then all actions are psi. Psi was e to the power h. So that tells you that the moding of the operator x is e to the power whatever I can't remember, minus I alpha by 2h plus every integer. How do you include beta? That. Okay, I didn't. Right. Okay. So you would include beta in the usual way. So beta is a charge. Okay. And so you would have a twist depending on what that charge was. So this thing would be twisted by the charge of e to the power I alpha plus n with a beta. So it would become an alpha plus 8 times beta. You include beta the same way that you included beta for the fermions. How do we include beta? You just said every state of charge q gets a factor e to the power I beta q pi. But the charge of all states here is clear, right? Because the charge is just translations in the bosons. Okay? So the simplicity in this bosonic language is that the oscillators are trivial. They carry no beta charge. Okay? And basically everything in the oscillator sector is totally trivial. Everything interesting happens in the zero mode sector. That's a single sum over integers. But then that's a simple process. Okay? This is a simple exercise that we could try to do if you were interested. It's a simple exercise in Poisson distribution. Okay? And it gives you what you want. Of course, it's a technical way of saying it. Is this clear? Do you want to try to do it? Okay. Okay. See, the only thing that this point is that the only thing that gets modified from the usual free boson is the zero mode sector. Okay? And the zero mode sector, instead of becoming an integral, is a sum. Like it's a sum. With moding alpha plus integer, or alpha by 2 plus integer. So that has energy alpha by 2 plus integer over x squared, has charge alpha by 2 plus integer into beta, and the contribution into beta. So it's a simple quadratic in the exponential sum. Okay? Anything that's quadratic in the exponential can easily be Poisson result because you know how to do the Fourier transform for us. It gives you back a it gives you back something in the same form but from different values. And basically the form. Okay? Yeah, so that's a technical way of seeing it. There's probably a physical way of saying it. Okay, which I haven't. Okay, so in today's lecture, we're now going to start trying to generalize our previous discussion. Okay, so all of you have heard that there are 5 well-known, consistent 10-dimensional superstring groups. These 5 are the type 2A and type 2B theory, type 1 theory, and the heterotic SO32 and the heterotic EX+E. Yeah, all of you have heard this statement. Okay, so so far what we have done is to construct those so far only 3 levels. So the introductions will be simple because we know how to work. Okay, well, what we have done so far is to construct type 2A, type 2B. So our plan for the next 2 lectures is to construct the other 3 famous ones. Okay, and in today's lecture we're going to try we'll move towards constructing the type 1. Now, the type 1 theory is obtained by taking type 2B theory and modeling this theory out by a symmetry of the theory. And that symmetry is the exchange between left and right. Okay? Notice that unlike the type 2A theory, the JSO protection of the type 2B theory was the same on left and right. Okay? So, this modeling out is a symmetry of the theory. We will study it carefully as we go along. We'll see the symmetry of everything is important of the BRST carbon, so on. Well, it's just clearly a symmetry of the free action of the torus. Okay, so one might attempt to try to make a theory by modeling the worldsheet theory out by this orientation reversal. Now, over the last year when we discussed the bosonic string, we could have tried the same construction with the bosonic string. Okay, I didn't do it because somehow we never got to it. The bosonic string, but that's what this lecture is going to do. Okay, we're going to back again to the bosonic string before we get confront a few additional complications with the superstring and try to play this game. So the bosonic string also has just a closed bosonic string has left movers, has right movers, and one can try to model the theory out by orientation reversal, exchange of left and right movers. So let's see exactly what the symmetry that what we're going to try to model out by. We're going to exchange, x of sigma will be set equal to x tilde of 2 pi. Okay, because the action has, because the derivatives in the action are quadratic in sigma, each derivative in sigma picks up a minus sign, but the 2 minus signs become a plus sign. This is symmetry of the action. Okay, but clearly, since something that's moving forward in sigma all the time moves backwards in 2 pi minus sigma, right? It exchanges left movers with right movers. Okay, you can clearly see that by plugging this into the expansion. So if we plug it, so let's do that. We have the expansion was, if you remember, we had sum over n e to the power I n tau minus sigma with alpha n plus alpha tilde n e to the power I n tau plus. Okay. Now what we're supposed to do is, in order to get the exchange between the x and the one. Now what we're supposed to do is effectively replace sigma by 2 pi minus sigma. The 2 pi does nothing here. E to pi and 2 pi is 1. But the other things flips the sign. Okay? So the thing that we call alpha n in the x expansion is referred to as alpha tilde n in the x tilde expansion. Okay? So this orientation reversal operation, what it does is takes alpha n from tilde n and alpha tilde n. It again changes. Okay. Now, what we're going to do is try to study the partition function of the unoriented string. So, the bosonic string with projected onto states that preserve. What we're going to do is take the symmetry and gauge it. Okay? So, projected onto states that have charge +1 under this orientation action is referred to as the unoriented string. At the level of the partition function, what we're going to do again is the trace over the inverse space of the bosonic string. But we get a 1 plus omega by 2. This is projected onto omega is equal to +1, where omega is the operator as this. Times q to the q bar. Q to the n0 q bar. What we're going to do is to try to compute this partition function. What we're going to do is to try to compute this partition function and to interpret it. Okay? But before we do this partition function calculation, I'm going to show you some geometric gymnastics that allow you to think of the worldsheet that describes this partition function in two different ways. This geometric gymnastic is the equivalent of the simple geometric gymnastics for the strip. Remember, the strip could be thought of as either a one loop of open strings or tree-level exchange of closed strings. Okay? This is a closed string state, a boundary state. This is a closed string boundary state. You have tree-level exchange of them. Or you've got one loop of open strings. Okay? And these two different ways turned out to be useful because it turned out that the partition function of the open string, when we acted on the modular transform, gave us something that was most naturally interpreted as this exchange between closed string states. Okay? Something similar is going to happen to this partition function. The partition function of the unoriented string. Okay? So what I want to do is try to convince you. What I want to do is try to give you the picture of what you expect before we get to the details. So let's look at the worldsheet that describes the partition function of this. Okay, as usual, what we do is to look at, we'll break some two different particles. The first one is just half of that of the bosonic string. The second one is half of that of the bosonic string, but with this omega inside. Now what omega does is reverse the orientation of the string. Okay? So instead of having a torus, what you have is an object such that this side is to be identified with this side. But this side is to be identified with this side with the orientation of this. Okay? So you take a rectangle, identify this side and this side as a drawn arrows, but identify this side and this side as a drawn arrows. That gives you the surface over which we want to do our path architecture in order to compute the second term in the strings. This surface has a name, it's called the triangle model. Okay? And I want to give you a second representation of this, which is geometry. Okay. Well, the movie strip is if this was these were a strip. If it was a strip. This is not a strip. This is a cylinder twisted. So that's it. And this is identified this. Okay. So let's look at the geometry. No, there's some trial and error here. I never remember which side on which part. But we'll see that soon. A couple of minutes. do is to take the surface and represent it like this. This is equal to, now I'll draw another line in the middle of this. Just halfway in the middle of this. Okay. And here, I'll break this up, and this is equal to this. This is equal to this. This is equal to this. And this guy is right here, draw for it. So this is equal to this plus just these two surfaces with the identifications as it here. I've just cut it and reminded ourselves that these two are arms, right? Now, the next thing I do is turn this guy around and join it. Okay? So I turn this guy around and I join it here, and so what do I get? Is equal to, so this guy was this guy. I've turned it around and joined it here. So once I joined it in orientation preserving manner. That's why I turned it around. So there's nothing special about this surface. No. But this guy is flipped around, so it goes this way, and this guy goes this way. Almost a torus, but you see, on this edge of the torus, but it's not quite a torus. It's like a cylinder with something funny. You see, firstly, this edge is not identified with this edge. This is 3 and this is 3. This is 4 and this is 4. So, what we've got here now is a cylinder, but not quite a cylinder, because along the side of the cylinder, there's what people call a cross cap. That is, this half of the circle is identified with this half. So think of cylinder as you view it like this. This is the cylinder we view. Okay, so this part is just regular identification. Okay, roll it around, now we've got a cylinder. But what you see is that what you're supposed to do is take the circumference of the cylinder, come up and say, whatever happens here also happens here. Okay, so if I draw a line through this, people normally draw this across, then at this point is identified this point. This point is identified this point. You see, we've got periodicity, we've got this identification on this on the surface. That is, our periodicity in this yeah, okay, so basically it's what you see, it's only at the boundary that this periodicity is imposed. And we impose this periodicity around the full cylinder, then we would just got cylinder properties. Is that clear? Suppose you have a cylinder of radius r, and we said, let's impose periodicity around half shifts along this radius r. That makes a cylinder of radius r by 2. So what is a cylinder? Just the periodicity. But that's not what we're doing here, because we are forced to impose this additional periodicity, but only at the boundaries of the cylinder, not at the bulk of the cylinder.
If we like to think of this as a cylinder with different boundaries joined together.
Joined together,
It's like
yeah, something like that. You see, it's not. But Well, it depends on what you mean by closed off.
Like, okay, I take this identification as
Right.
like joining the.
Yeah, I think you could sort of think of it like that, maybe. I mean, what it is in terms of functions is clear, right? That any function of this object has to respect half periodicity on the boundaries, but only the full periodicity in the boundaries. Okay? Now, this kind of identification of the atrial cylinder is called a cross cap. So a cross cap because people draw this cross. And now we see what the second representation of this partition function of the inserted omega is. The second representation is just a cylinder with two cross caps. Okay? If we took the original torus to be of 2 pi and tau here, the moduli of this guy have this being 2 pi, 2 tau, and pi. Okay? So, if we chose to rescale so that this guy becomes of size 2 pi, then this guy becomes of size this is 2 pi. Well, 2 pi tau. We're not mentioning our 2 pi. This becomes 1. Everything's in units of p, right? That's one is half. It's 2 tau into 2 pi. So that's one is half. So if this was 2 tau. If we divide everything by 2 tau, we will get 1 over 4. Okay? So the bulk, this will be a closed string of size 2 pi, propagating over a time 1 over 4. World sheet time 1 over 4. Is this clear? So we should expect that there is a representation of the partition function that we're about to write down. That there is a representation of the partition function that we're about to write down, which can be written in terms of closed strings, propagating over a world sheet of time length 1 over 4 tau. We see that that's true. Is this clear? Okay. Now, fine. Let's move away from pictures and start trying to calculate. Any questions about it?
So is this object like?
Remember, Jyoti point never liked it before. Go on.
Like, is this object like topologically same as a sphere, like with some special points?
No, it's not topologically same. Oh, but special points. You see, once you allow special points, the cylinder is the same as the sphere with two special points. Yeah, so in some sense, with special points, that's true. Yeah. But topologically, it's distinct from it. I mean, clearly distinct. We'll discuss in a bit what genus was. But now, I mean, the genus is basically, it's there. You see, this is a one loop graph, so it should scale in G to the n. Okay, so you should. Now there's some people have this way of, right? I think people say this is the kind of thing which is within my walls. I think people sometimes talk of this as a sphere with two cross caps inserted. Okay? A sphere is 1 over G squared. And so this tells you should assign each cross cap a factor of G. because it's a one loop graph, which is contributed to the function. It's a partition function of free states. Okay? But clearly this should be thought of as a genus distribution. This search by itself should be thought of as a genus distribution. Okay? So if you want to think of it as a sphere with insertion of these cross caps, then you should assign the cross caps a factor of string number. It's like that. You don't have to think of that. Okay? It's the same way that a boundary. If you want to think of a cylinder as a sphere with two special things making its boundaries, these boundaries should also be ascribed factors of G. Okay, so that's it. Okay, so that, I'm not sure any of that is very useful. Okay. Okay, so let's go about trying to compute this. So what we want to do is to compute trace of omega by 2 q to the power 0 q bar 1. Well, yeah, we will impose all the same. But at the moment, yeah, you'll see that level matching is automatic. In this, we would impose the same level matching, but that's only right for 1 second. As you will see. You see, at the moment, what we're doing is calculating the worldsheet function. Level matching in string theory is done when we do the d2 tau integration. So at the moment, we're not addressing that question. Okay, but you'll see as we go along. What? No, the trace is the worldsheet case. We're computing the worldsheet partition function, and then we insert it into the appropriate d tau integration. Okay? That will be the case for the 1, but as you will see here, there'll be no issue. We'll see that in a minute. Okay, so let's try to understand this trace. So what is this trace? You see, this trace has this factor of omega. Now, omega interchanges left movers with right movers. So suppose you've got a state, okay, in which you've got certain excitations on the left moving side and other excitations on the right moving side. This state is going to be inner producted not with itself once you have this omega, but it will get the contributions to this energy from here. And then will be inner producted not with itself, but with the state which interchanges left movers and right movers. Okay, so suppose you've got some psi on the left moving side, some abstract thing that, and some psi tilde. This trace will be proportional to psi tilde psi and psi tilde. And because you first interchange left and right, and then join again. Now, if we do our trace with we do our trace over orthogonal states, as we always do, this will only be non-zero psi tilde equal to psi. Is this clear? You've got some Hilbert space of left moving excitation. You've got some Hilbert space of right moving excitation. They're the same. That's why it makes sense to have two suggestion. Okay? Now, imagine where we're working on an orthogonal basis. Suppose you are in state M and N, where M is not equal. Then that does not contribute to this trace. Because this trace takes the state, propagates it and weights it with respect to its energy, and then switches M and N. And then takes the inner product. So that gives you the inner product of N with N and N with N, both of which are 0 if M is not equal to N. Is that clear? So this trace gets contributions only from those states that have equal states in the left moving and right moving side. Of course, the 0 mode is neither left moving or right moving. It does its own thing. This orientation business acts only in oscillators. This acts only in sigmas. 0 mode is not a function of sigma. Okay? So, what are we going to get? What we're going to get here, let's say hyperbolas are not doing independent things, you have only one parameter, not the additional tau, which will couple the difference between them. That's not the other imaginary. So, what we get here is trace q to the power 2l of e to the power minus 2 pi 4 pi times l naught over the trace of just the left wings. Okay, times the zero mode contribution expression. Okay, let's remind ourselves of the zero mode contribution first. And unfortunately, factors of 2 will turn out to be important. So we have to be a little less cavalier over the zero mode contribution than we have often. So I'll remind you also about the zero mode contribution. The zero mode contribution is simply e to the power minus 2 pi t times the Hamiltonian dual zero mode. Now remember the Bosonic string has 1 over 2, what is 1 over 4 pi alpha prime times, and 0 mode part is x dot square times d sigma. So that will get rid of 2 pi. So that's it. As far as 0 mode is concerned, it's 1 over 2 alpha prime times x dot square. Now this is like long relativistic quantum mechanics. To spectrum is, this is like the role of the mass is taken by 1 over alpha prime. So the spectrum is alpha prime p squared prime. So the zero mode contribution is integral d b by 2 pi to the power, it's 2 pi, I have no idea. I suppose 2 pi to the power p. And then e to the power minus alpha prime p squared prime. Okay? And now, it's not going to matter for any relative factors, but just to show that we can, let's see if we can get this completely right. I'm not sure we've ever tried to do it completely right before. Can anyone remember what is e to the power minus x squared? Root pi? From minus infinity to infinity? Root pi, excellent. So we get a factor of root pi to the power d. But we also get a factor of square root 2 by alpha prime to the pi. Okay, so we get square root 2 pi by alpha prime to the power d divided by 2 pi d. Well, and then of course, and then I should have had, I should have had this multiplied by 2 pi. Yeah, I should have had the temperature, yeah. So this is multiplied by 2 pi t. So I want another square root 2 pi in the denominator. I'm suspecting it just becomes this. Sorry, what does this become? This is just a pi. We get a pi in the denominator, pi cancels the pi in the numerator, right? So we get, and then of course we get t to the power t to the power d by 2. Okay. So the zero mode part should be 1 over 2 pi d t to the power d by 2. I'll check this. Okay. I will only need a relative factor, so if it makes a 2 pi mistake about it, just convince ourselves yes. Well, there's an alpha prime. The alpha prime should also be the denominator. So square root alpha prime is the denominator. Alpha prime t equals to right. Sorry, this is quickly. Correct. Pi square alpha prime tau to pi over. Yes, okay. Good. So what do we have then? We've got half because of the half that we have omega by 2. And we have 4 pi square alpha prime t to the power d by 2. And then we've got this trace. This trace of e to the power minus 4 pi t L0 just over the left-hand sector of the bazaar. Okay. Now, this is our answer. And this answer, of course, we know how to compute, right? So, this guy in particular is e to the power 4 pi t into 1. That's from ground state energy, because N0 has energy minus 1. Sonic state times product over N, 1 over 1 minus q to whatever. E to the power minus 4 pi t n, and then this whole thing to the power. D is 26. I assume that value is power. Okay. Now, what we're going to do here, what we're going to do is to analyze this one loop diagram in the limit. Okay, and there is some I won't try to sit and derive it for you now. Maybe in the subsequent class. We will also have to work out the measure over moduli space for this path integral, and it turns out that this is basically the same as the same, which was dt by 2t. Okay, you get dt by 2t for this. I will just assume this is true. Perhaps in a future class justify it. It's the same kind of consideration. It's probably easier. Okay, good. So the full answer now, the space-time partition function, the contribution to the space-time partition function is dt by 2t. Then there's this initial factor of half, so 4t, and 1 by 4 pi squared alpha prime t into d by 2 into e to the power 4 pi t into product over n 1 over 1 minus e to the power minus 4 pi t n the whole to the power n. This is the contribution of this Klein model, okay, to the one loop partition function in space time. Now, what we're going to try to do is to take this contribution and examine it in the limit that was problematic for the cylinder, namely the limit of small t. Okay. In the limit of large t, this thing has some sort of divergence from the tachyon, but that we know. But in the limit of small t, You know, we're going to play the same game that we played for the cylinder. We're going to play the same game that we played for the cylinder and try to understand what happens to this integral when t becomes very small. Okay? This is not a useful form of the integrand when t becomes very small because all of these states are very light, there are plenty of them. So what's useful is the modular transformation. So that's what we want to do. But here we're in luck because the non-trivial part of this function is exactly what we get for, is exactly what we get on the closed string if we set tau is equal to e to the power minus 4 pi. Okay? So let's remind ourselves of that. Suppose we work with the closed string and set tau is equal to tau bar is equal to 4 pi di. Okay? Then what will the partition function do? We get then what will the partition function do? From the oscillators, we would get 1 minus e to the power minus 4 pi t n. Ghosts, we do the usual thing. The road of the ghost is just to cancel the two transitions. Sorry, these guys. Yes. These are the transfers. Sorry, I said traces. Good. Okay? Now what I want to do is to deduce what happens to this partition function as t becomes very small. So I want to use some identity that I'm going to do. And then okay? Of course, one thing is basically a theta function identity, but I want to derive it using physics instead of remember theta functions. Okay? So what are we going to do? See. Well, eta function. It's basically an eta function. And there's some modular transformation property of eta, which is what I'm going to use. But let's see how that goes. Okay, you see, suppose we have the closed Platonic string and tau is equal to tau bar is equal to 4 pi t. Then what would we get? We would get the partition function would have an extra factor of 2 because this is 4 pi. So 8 pi squared alpha prime t to the power b by 2. That's what the 0 was. Then we would have had, because of this extra distance here, we would have had e to the power 4 pi t times L0 plus L0 bar, but that's minus 2, so that's into 2, so let's call that 8 pi t. And then we would have had this e to the power minus 1 minus 4 pi t n, the whole thing squared, the whole thing raised to product. This would have been the worldsheet partition function of a closed Platonic string at tau equals tau bar is equal to, sorry, the 2 pi second. Sorry. Is this clear? What do we get? We get q to the power 1, q to the power minus 1, q bar to the power minus 1. But q and q bar are each e to the power minus 4 pi t. So we get e to the power 8 pi t from there. This is the 0 mode part. So the vacuum part. Well, no, I'm calculating this worldsheet partition function at this special point in mind. Okay, so at this special point we have this from the vacuum energy, and of course by construction we have the same as this, except we have the square of it. Because we have separate contributions from left movers and right movers. Okay? So of course, this, because it was just a left moving side, is the square root of this amount. But, because the 0 volt part is just a 0 volt part, apart from some irrelevant factor of 2, the 0 volt contribution here and here are the same. Okay? Now, this object was modular independent. Because it was a partition function on a torus. A well-defined bosonic path integral. Well, this object by itself is a modular independent. Okay? Therefore, this object is equal to itself under the exchange t goes to t by 4. T by 4 is this 2t. Tau goes to 1 by tau goes to minus 1 by tau is symmetric. Tau goes to 1 by tau will take 2t by 2. Let me say that. Okay? If I take tau goes to minus 1 by tau, in this formula, I get the same answer. But tau is equal to I to I. Okay? So minus 1 by tau is equal to I by 2. Okay? Which is equal to 2I over 4. Right. Okay? So, this object is the same. So if I define S is equal to 4 by T, okay, then this function is the same function of S as it is of T. This partition function, where I replace T by S, is the same object as the partition function itself. Okay. So what do we have? So we have that from modular, now of course these constants don't matter for modular invariance. So we have that from modular invariance, S, so let's write S 1 over e to the power d by 2 times 8 e to the power h by t times product over n blah 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 2d is equal to the same object replaced by s, where s is 4 by t. D by 2 e to the power h by s product over n blah blah blah. Now we're interested in that object, which is the square root of this object. So let's set the square root of this equation. Okay. We get d by 4, we get 4 pi t, and we get rid of this 2. 4 pi s, no 2, so d, and s to the power d. Now, on the left hand side here, we have basically this, except we have e to the power d by 2. Okay? So let's multiply this by t to the power d by 4. And multiply here by t to the power d. Okay? Then, this is the object that we wanted. Yeah? And this is the answer. This is the answer to the S. Oh, and I made one more mistake. This D is the D here is 26, whereas the D here is 24. That is a serious mistake. Let me just replay. Because the 0 mode runs over all dimensions. Now how do I correct for that? I'll call this D plus. Plus. It's against. I'm sorry. Okay, let's see where that fits. So, I'm going to ask you in your mind today. I maybe should just go to the result. But anyway, let's go ahead. Okay. So, where are we? Now, this D into S. This D into S here. This D into S here is basically 4. So, what that gives us? There's no modular invariance on this triangle. Two sides are different. It's like similar. Was it 4 by 3 or 1 by 4? Yeah, 1 by 4. Thank you. Okay, sorry. So T gas is 1 by 4. Okay, so what do we get from here? Finally, what do we get from here? We get 2 into 13. Okay, so we have the 0 mode term. So, right, this is 2 into 13. Times product over times e to the 4 pi s. Okay, that product over n, this is 1 minus e to the power minus 2 pi ns. The whole to the power 24. Okay? And we're still left with only when we have a dt by t. Actually, we've got an extra t somewhere. Where is that?
This is the on the layer.
But this is the, it should have become t squared. That is this. You see, that is a plus 2. Let me say it again. I'm sorry. I'm sorry. I'm very sorry about this. Let me not work with D. Let me write with 13. Okay. We had. You see, the thing that is modular invariant is 1 over t to the factor b times this thing squared. This thing squared. Okay? Now, I'm sorry. Stupid. Just give me 1 minute. Where's my extra power? Just a minute. Sorry. I'm really sorry. Let's look at the whole thing. I'm sorry. You see, what is modular invariant? The thing that's modular invariant, the closed string partition, if you take a single free boson on a torus, that is a modular invariant. So sorry. Let me say this. Okay. Consider the partition function of a single free boson on a torus. That object is modular invariant. Okay? That object has as many powers of p. That object has as many powers of here. If that object d is the same here as here. That's the object that's modular invariant. Okay? Now, it is true that when we are interested in this calculation in string theory, we have one extra zero mode compared to the oscillator stuff. And that all feeds into the net modular invariance once we absorb that extra factor into the measure of our moduli space. You see, so let's forget about all of that. Let's just return to the question of what was modular invariant. So the thing that was modular invariant was this object with 20. Okay? So, as far as we are concerned, this object with a 1 over t to the power 12 times this to power 4 was equal to 1 over s to the power 12. Okay? Times this to the power 24, everything with x. That's what modular invariance is. Is this clear? Okay. So, and this is 24 by 2, so that's 12 by 2, so that's 6. We originally had t to the power d by 2. I'm sorry, I've succeeded in confusing everyone apparently. Look, suppose we were calculating the closed string partition function of the torus. Okay, forget the dimension secure string. A single free boson. Let me do it with 1. Let's set B2 1. Single, the partition function with a single free boson, sorry, okay, has a power of 1 over square root times the 0 point contribution times this product over all n, but this square because left and right. Is this clear? The partition function with a single free boson takes this schematic structure. It is 1 over 24. That's the subject. Okay? Now, this is formula element. Okay? So this will be equal to the same thing written in terms of S. So it will be 1 over square root S times sin 0 1 contribution times this thing squared product over n. Now what we are going to do is take this formula, square root, and multiply by, take it to the power 20. Okay, so what do we conclude? We conclude that 1 over t to the power 1/4. This product to the power n without the square, no square, to the power 24 is equal to the same thing with s. Is that clear? Because I just taken square root of this and just multiply this over, taking this equation to the power of 2. So the first equation is true, this one is also true. But now see, what power of t do we have in this formula? In this formula we have 1 over t to the power 24 by 4. Right? 1 over t to the 4 to the power 24. Okay, so we have 1 over t to the power 24 by 4. But where we actually wanted to use the formula, what power of t did we have? We had 1 over t to the power 24 by 2 plus 1. Because we had 1 over t to the 30. The thing that came from 0 mode of string theory had 1 over t to the 30. Okay? So we have to take this formula and multiply it by 1 over t to the power 24 by 4 into 1 by 2. That gives us what we actually had for the unoriented boson string. Okay? So on the TS, on the S side, that is equal to 1 over S to the power 24. Sorry, 24 by 4 into T to the power 24 by 4 into 1 by T into the oscillator zero mode part, the zero vacuum energy part with T replaced by S. Okay? This part together gave us this 2 to the power, this factor of 2. Okay? Some 2 to the power 12. But in addition, we're left with an extra factor of 1 by 2. Okay? That's combined with what we had in the measure. That combines with what we had in the measure. So we have dt by t. We've got an additional factor of t, so that's t squared times e to the power whatever it was. Was it 4 pi s times product over n 1 over 1 minus e to the power minus 4 pi s. Then we have this 2 to the power 12 factor. And now we're going to replace this by a ds. Okay? Remember, s was equal to 1 by 4t. Was that right? S is equal to 1 by 4t. So, we get an additional power of 2 to the power 14, but then there was a half from the projection. So 2 to the power 13. So 2 to the power 13 into the 8 pi alpha blah 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 that we have. Okay, somebody remind me what that was? Just the pi's and alphas. Was it 4 pi squared alpha prime? 30. Okay. Into s times e to the 4 pi s into product of n 1 over 1 minus 8 pi 4 pi. Okay, I'm sorry for the mess ups. I think this is finally the results. Okay. It's s, where s is equal to 1 over 40. We're just supposed to replace t by s. Right. But now we're doing a modular transformation. We're not rewriting the same formula in terms of s.
Oh, you're using modular transformation in this part of it and you're doing the proper.
Only in the measure we need a change. Right? Okay. So now we have the same story as we had for open string exchange. You see, we were interested in what happened to the we were interested in the ultraviolet divergences in this effectively open string or flying body channel. That's what happens at very small values of t. But that's the same thing as what happens at very large values of x. Okay? And what happens at very large values of x? Of course, this is part of the right? So what happens at very large values of x? First, we have this dominance for the tangent. That will go away when we consider the superstring. We kept saying that last year. This time we'll actually see that very soon. We understand the superstrings. Okay? So we see this. However, the really serious thing that we had was that there were terms, and then there are terms where you expand this sufficiently so you get negative exponentials, you get convergent integrals. But if you remember, the term that was really serious was the term in which these exponentials cancel each other. The one factor. That was a tadpole. We analyzed this in great detail, not entirely to Jyotirmoy's satisfaction, if I remember right, a few months ago. So what's the coefficient of that tadpole? The coefficient of that tadpole is 2 to the power 13 times 4 pi squared alpha prime to the power 13 times 24. This is the 24 states when you accept this. Okay? So, what have we done in this lecture? I'm sorry, I intended to tell you many more things about the annoying in this lecture, but I got stuck with this stupid SNT. Okay? So what have we done in this lecture? We've discovered something. We've discovered that if you add unoriented strings into your spectrum, then they behave in many ways like open strings. Okay? That is this you take the integral over the slide bottle is an integral over a real rather than a complex parameter. So we don't have this fundamental domain of the modular region. Okay? So we have a potential divergence as t goes to 0. This potential divergence as t goes to 0 as for open strings can be reinterpreted by a modular transform as a potential IR problem in the closed string sector. This IR problem is a problem of creating tadpoles, and we've seen that introducing oriented strings into the spectrum does give you tadpoles for master states. Remember that the tadpole was simply the problem that if you wrote down this space-time effective action, there would be terms in the space-time effective action for massless modes that were linear in these modes. Terms that are linear in massive modes, it's not a problem, but massless modes are severe problems. So you don't know it. The vacuum is significantly different from what we expected. Okay. Now, therefore, we've concluded, this is the analog of the one loop torus calculation closed strings. And we conclude that the oriented bosonic string is just an inconsistent theory. So the inconsistency is worse than that here. The analog inconsistency, as we will see for the superstring, will remain because of the stack. But remember that we had similar kinds of tadpoles when we studied open strings. So now this leads to the obvious question. Can we study a theory which has both open strings and unoriented strings? It's an unoriented string theory along with space-filling brains. Open strings live all over space. If we study this theory, can we get this tadpole to cancel? Can it be that the sources for all massless modes from this what's called an oriented mode, the fact that we have this unoriented string theory, cancels the sources for massless modes coming from open strings? And the answer turns out to be yes, but unfortunately we won't be able to see this in this class, but let me just give you the advertisement. It turns out, so the first thing we have to do, of course, is to study open strings in an unoriented theory. Right, because we're committed to dealing with the unoriented theory, that will have some impact on the open string sector. Because we've got this orientation projection, the closed string sector means that's also there in some way in the open string sector. Okay? So we have to study what the orientation projection does in the open string sector. And we will see that one of the consequences is that on open string theory, instead of having a UN age group, you have there are two choices. You get either SPN or SON age groups. And what we find is that the net tadpole will turn out to take the form 2 to the power 13 plus minus n or minus 1 square. Where minus is for SON, plus is for SPN, and n refers to the number of D brains you put in background, the number of jam pattern indices of your string. Okay? Or is it 2 to the power 13? Yeah, that's okay. Right. 2 to the power 13. We'll see this in the next class. Okay? So, we get a contribution from this part will be the contribution that we just discussed. Yeah? The part that's n square will be the contribution from the open strings, and the part that's linear in n will be the partition function from the Mobius string. That is open strings with the orientation projection. Come. Okay. So we'll see this in a bit. Okay. So it will tell us that the theory with unoriented strings and open strings for a very specific number with a gauge group SO2 to the 13 is a tadpole free theory. SO2 to the power 13. Okay. Now this 2 to the power 13 will become 2 to the power 5 for the superstrings, D by 2. Okay. So that's SO32. Okay. The analog construction of that for the superstring will give us a tadpole free superstring with gauge group SO32, and that will be tadpole theory. So we'll study that next class. So, please.
Oh, what he's doing is he's looking at the. Sorry.
No, I don't understand how the zero mode match.
You understand how the zero mode? See, I can tell you how much I got.
I'm getting a Q. See, okay, first of all, is it correct that in the oriented theory, okay, in the calculation, you get a 1 over q square before doing any model transformation. You have 1 over q square and the 0.